So hello everyone, this is lecture 2 for the atomic physics. In the last lecture we were discussing about the Bohr model and I hope you get the good idea of that. And if you are still having any doubt, you can leave the comment in any of the video and I will definitely reply. And I must know that if you are understanding or not, because I am just trying to keep these lectures time efficient. So that's why I'm just doing them time efficiently. So let's start today's lecture. So we discussed in the last lecture the postulates of the Bohr model, and in that we studied that the electron inside the atom will follow the classical equation of motion, and the difference is now the orbits of energy will be fixed, and there will be means those orbits will be stationary orbits because if electron is moving, then definitely it is accelerating and it must emit radiation, but is not emitting because these are the stationary orbits. And we understand that radiation will be emitted when the electron will jump from the higher state to the lower state, and that the frequency can be find for the photon in this formula, change in energy divided by h. And then in the third postulate we studied that angular momentum, if the orbit is fixed, then definitely angular momentum will be quantized or discrete also, and that will be given by this formula nh by 2 pi. And I told you that I will give you the proof of this. Now see, Bohr understand means he took this assumption that electron will moving like a wave also, and it must complete this wave. So it means that lambda, if there is a wavelength, then this complete circumference must be integral multiple of the lambda. So 2 pi rn will give you circumference must be it must be n lambda. From here you can just see that lambda is h by p using de Broglie. Now this p rn will give you the angular momentum, and that will be equal to nh by 2 pi. So that's how you can remember. Now in the today's lecture we will see all the mathematical formulas can be framed. Means we will find the radius and we will find the velocity and the energy of the orbits. Because we are also using the classical equation of motion, that's why we can just apply them, and we'll find the radius, velocity, energy and all. So first it is angular momentum is nothing but mvrn, and vn is just denoting that for nth orbit, and that must be equal to nh by 2 pi. We just denote this h by 2 pi as h cut. So from here you can find that vn equal to nothing but nh cut by mrn. So that's how you can find the velocity. Now we know that anything rotating in anywhere, that must be because of some centripetal force. So what is centripetal force here? It must be coulombic force that will be between the charges. So if this is your nucleus, that must carry the charge, and Z will denote the number of protons inside. So it will be Ze, and for the hydrogen it will be Z equal to 1. So we just take a general expression for any atom, so it will be Ze, and there will be one electron in the orbit. So Vn is nh squared by mrn. So this is your centripetal force mv square over r. That is equal to coulombic force Ze multiply E divided by 4 pi epsilon naught Rn square. Now from here you can just see Rn will cancel out, and from here Rn will be Z square by 4 pi epsilon naught mvn square. So you must not remember these all formulas. I will tell you which is need to be remembered. So only remember those formulas. So Rn will be Z square by 4 pi epsilon naught mvn square, and it will be equal to this. Just substitute the value of Vn from here in here, and you will get the formula for the Rn. This one Rn will cancel out, and you will get the formula for Rn. This will be this. Now if Z equal to 1, this formula will reduce to this, and this is called the Bohr's orbit, and this value is nothing but 0.52 angstrom. So you don't need to remember all of this, you just need to substitute this, means keep this n square by Z outside, and whatever remaining is called the Bohr's orbit or the Bohr's radius, that is 0.52 angstrom. So it will be this. Now Rn will be given by this formula. So for any Z and for any n, you can calculate the Rn directly. So this formula must remember, you must remember this formula. Now we have Rn, so we can find the velocity also Vn. Vn can be find it directly, means here we have the formula nh cut by mrn. So just substitute the value of Rn from here, and you will get the value for the Vn. That will be E square Z by 4 pi epsilon naught nh cut. Now this will be your means just multiply with C in the numerator and C in the denominator, and you will get this term outside, and whatever remaining here is called the fine structure coefficient. So you must remember this. This is means not the formula. You must remember that this is called the fine structure coefficient, and we denote it by the alpha. So the formula of the velocity will be Z alpha C by n. So this must be remembered. I mean this formula must remember Vn equal to this. And now the alpha will be given in the question if they ask you. So you can just directly put them and find the answer. So alpha will be this, and the value of this is fine structure coefficient in the SI unit will be this. Normally they give you E square by h cut c, so they give you in the some books it is written in the series units, but you must remember this SI unit value, that is this equal to 1 upon 137, and this is called the fine structure coefficient. Also this is a constant. So that's how you can find the velocity. We have find the radius and the velocity. Now let's find the energy of the orbit. To find the energy, we must find the potential energy and the kinetic energy separately. So see, to take this for this electron, we must take this electron from infinite to this radius Rn. So the work done in doing this work means carrying this electron from the infinite to Rn. That work will be stored as the potential energy. So we'll just use that formula for potential energy. So we integrated infinity to Rn and negative sign F dot dr. So just substitute it, and F we know is nothing but, means you know how to find the force between two charges, that is ZE multiplied by E divided by 4 pi epsilon naught, and Rn square, and Rn will be integrated from infinity to Rn and dr. Now just substitute the value and see, this one charge is negative and one is positive, that's why this negative will turn to be positive here. And now when you integrate this, you will get a negative sign again, because this will be 1 upon x square dx, that will give you x 1 upon x minus 1 upon x. So that will be this. Now you must know that potential energy is always negative inside an orbit, means something is rotating around something, that must be have negative potential energy because it is bound, and bound motion always has the negative energy. If you need to take it outside this orbit, you must give it a energy to make that zero, or the positive energy. So this is your potential energy. Now substitute the value of Rn from the previous expression. So that will give you, this is your potential energy. You don't need to remember this formula again. So now the kinetic energy will be simply half mvn square. So because now we are not considering the relativistic nature, it is a simple. So now substitute the value of Vn, what we already derived for the Vn. So you will get this value. And now see, in this and this, what is the difference? If you take the mod of this potential energy is simply half of this. Means half of potential energy will be kinetic energy. You can see that half multiplied here will give you this value. So the kinetic energy is nothing but half of mod u. So you must remember this expression also. Now total energy will be sum of kinetic energy and the potential energy. So if you take the sum of this value and this value, it will give you minus of this. So total energy is nothing but minus of kinetic energy. So total energy is nothing but minus of kinetic energy, and kinetic energy is nothing but this, half mod u, and u is negative, so you will get here positive sign. It will be half un. So un is negative, total energy will be negative. So this will be equal to this. And now you can see that this expression, now value of this one is nothing but, that is Rydberg constant. We already know about Rydberg constant, so that is came from here, and we denote it by the r infinite. So I will tell you why we are denoting it with the r infinite. So this will give you the formula for energy. So what is r infinite? See, in this atom, we consider that this mass of the nucleus is infinite compared to the mass of electrons, means this is very much larger, or the infinite terms times the electron's mass. So that's why we consider this as stationary here. And now if it is stationary, only then we can just get these formulas. So that's why this is called the Rydberg constant for the r infinite. When this mass becomes finite and not infinite as compared to electron, then we will see that there will be we need to consider the reduced mass, because it will be like, if this is your line of axis, then you will get center of mass somewhere here, and then this will also rotating around it, and this will also rotating around it. So we need to consider the reduced mass then. But now we are considering that this is infinite times this, so it must be remain stationary here, and then we will get these formulas. So that's why this Rydberg constant is r infinite. So we will consider those formula also when we will consider them finite. First we are taking it as rest. So throughout this calculation, we have assumed that electrons are orbiting about nucleus and nucleus is at rest. This is possible only if nucleus is infinitely heavy as compared to the electron. Due to this reason, we are writing Rydberg constant as r infinite. So in place of this, we can write r infinite, and you know already the value of r infinite we discussed in the last lecture, that is 1.097 multiplied 10 to the power 7 meter inverse. So this will be this, and r infinite SC, you can find the value. So now this whole value will give you minus 13.6 z square by n square, and this energy will be in the electron volt. Means this is in the SI unit, but this will be in the electron volt. So you must remember. I hope you know how to convert the electron volt to the joule. So that's how you just get this formula. Now kinetic energy will be simply equal to the total energy, but in the positive sign. So it will be r infinite SC by n square z square, and potential energy is nothing but minus of, means it will be, from here you can see, it will be 2 times of total energy. Potential energy will be equal to minus, it must be negative sign must be there, so minus 2 r infinite SC by n square z square. So that's how you can calculate the different energies in the different orbits for the one electron system inside an atom. So you must remember these formulas. These are very important formulas. Now see, this is the case for when we are considering nucleus at the center and it is not rotating, means it has the infinite mass as compared to the electron. But now we need to consider the finite mass of the nuclei. So for that we will see that there will be this kind of thing, means this is finite mass, this is finite mass, so there will be center of mass somewhere here, and this will be rotating around it, and this will be rotating around it. So this motion will be something like this, means at one point it will be like this. So for this we need to consider the reduced mass. So we'll discuss in the next lecture that what is the concept of reduced mass. That is totally mathematical term to reduce two body problem into the one body problem. So for just now we will consider that whole mass will reduce to product of mm divided by m plus m. So this will be a reduced mass. Now there will be only one body rotating, so we can just consider the mu mass everywhere. In place of whenever or wherever we use the small m in these formulas, we will just replace this m with the mu and we get the same formula. So there will be no much change in the formulas. There will be just replacement of m with the mu. So we know normally that mass of proton is very much larger than electron, so normally it doesn't affect the calculation. We consider the nucleus as the stationary. So this is the case because the mass of proton is very large as compared to the electron. But now let's consider the finite thing. So if we consider the motion of the nuclei also on the finite mass of nuclei is considered, like then this becomes two body problem. In case of two body problem, expression of various quantities will not change except the mass of the electron is replaced by the reduced mass mu, that will be mm divided by m plus m. This m is the mass of electron and this m is the mass of the nuclei. So we know the formula for the Rydberg constant, that is this. Now for the any finite nuclei we need to find the Rydberg constant, so we'll replace m with the mu. So what we do, we just write mu here and multiply with m and divide by m. So that's how we can just write the Rydberg constant for my finite mass in terms of the R infinite. So what we do, we just this is your replaced m with the mu and divide by m and multiply with m. So this will cut out and this will remain same as we have used the formula here. Only the replacement is mu here. So why we did this? So we can just replace this mu here and m is here. So this is nothing but R infinite and it will be R infinite, and mu is nothing but mm by m plus m. So just substitute the values and this 1m will cancel out and this will go in the denominator. It will be R infinite by 1 plus m over m. So this is your general formula for the Rydberg constant for any mass system. So you know the value of this and you know the mass of this. Means for the hydrogen atom 1h1, how can you find? This m is the mass of electron and this is the mass of the proton. So it will be 1 plus me divided by mp. So for 1h1, this will be like this formula. And if it is a deuterium, it will be like 1 neutron and 1 proton inside the nucleus. So mass of the neutron is approximately equal to the mass of proton. So we can just write in place of this capital M 2 mp for the 1 neutron 1 proton. So for 2d1 this will be your formula for the Rydberg constant. And similarly you can find for the helium also, means helium has the 2 electrons in its orbit. When one is gone, then it will be helium ion He plus. Now inside the nucleus you will have 2 protons and 2 neutrons. It will be 4 mp in the denominator and simply mass of electron. So it is me here. Now similarly we can find the generalized formula for energy also. We have written for the reduced mass En prime. So in place of m we just use mu here and again divide by m and multiply with m. So replace this m inside and mu is here. So this will give you your again energy, which you already found this formula. Means here you have the formula for the energy. In place of m we will just write mu. Means in place of m you will write mu and divide by m, multiply with m. So you will get this formula, means mu is here and m is here. So you know the value, that will be this, and it will be mu by m outside. Now this will be your formula. You just need to find the mu. You know how to find the reduced mass. That will be simple formula, mm divided by m plus m, and substitute here. You can find the value of energy at any nth orbit. Now similarly for radius also we can just similarly we can derive, and you will get this formula. These formula you must remember. And if we talk about the velocity, then velocity doesn't depend on the mass of the electron or the nucleus. So that will be independent of that and it will remain same. Mass of the electron doesn't appear in the above formula. So finite mass of the nuclei considered will not be affect velocity in any orbit. It will remain same. Velocity will remain same. Now, well, we will end this today's lecture here, and in the next lecture first we will discuss something about the reduced mass. Then we will move forward to understand the two different atoms or different hydrogen like atoms. So that's for today. Thank you everyone.